detect this node split. And we continue making inserts. Then we're almost in the same case as before, and in terms of nodes and values in the nodes, we're in the same case. This is case 1 described before, and making these insertions, each we will have node splits when inserting n values, when inserting 2n values, when inserting 3n values, and so forth. So this can be detected, and simply if you detect 2 or 3 node splits in a row, let's say in I plus 5n, I plus 6n, and I plus 7n, then using this information you can guess there was a node split, and the algorithm is robust and it can handle this. The same conclusion follows, namely if in that event, if you made inserts until I plus 7n, then the tree configuration remains the one we wanted, and you know that the key k is on the right half. Only that instead of making n inserts, you made n 7 times or 5 times n inserts. And as I mentioned here, you need to redefine A as A plus 3n or 5n minus 1, and the binary search algorithm can continue. In the other case, if k is smaller, then we are in this case, and something similar happens. There will be node split at I plus n minus 2, I plus 2n minus 3, and so forth. So detecting 3 of these node splits in a row, it doesn't matter if they are these ones, will allow the attacker to know that he's in the second case and the key is on the left side of a node. Simply taking b equal to I will suffice to continue with the binary search algorithm. So similarly, this split detection algorithm combines with the setup. I didn't describe the setup algorithm, but let it suffice that they can combine. And is this a good efficiency? Well, we say yes, it is, because if you this attack takes is exponential in speed to compute a key. And if you compare 3 times the logarithm of n with n, then for high values of n, this it's 3 times the logarithm of n is much smaller. And this means that even if we tripled the time our algorithm takes, triple the number of inserts our algorithm takes, the algorithm is still efficient to detect keys. So this ends my description of the algorithm. I don't know if you have any questions, else I will move to future work, countermeasures. Okay. So how can we improve the attack? Well, there's several things we have in mind, and this is ongoing research. We want to keep on working with this. And the first thing we can ask is, can you take this attack outside the laboratory? Is this a real attack, a realistic attack? Well, we believe it is. However, it needs to be researched further. As I mentioned, we tried this attack from a station away, one switch away from the web server hosting the database, but we need to try other configurations. And also, well, split detection isn't very good. We have evidence making different insertion strategies that split detection can be made with fewer inserts. Say, instead of taking n or 3n inserts, we can take 2 or 5 inserts. But in our experiments, the tree configuration broke, and we couldn't continue to execute this. So we need to experiment further with MySQL. And to this, let me mention that we didn't have good documentation to know how B-trees work. So basically, we read the source code and played with MySQL, but there's no description, and we're unaware about the complete behavior of the indexing algorithms. So maybe there are some optimizations hidden that we didn't find, and profiting from these optimizations, we can make the attack much more efficient. And also there's heuristic optimization that can be made, and this we did experiment with, and this is if you know what's the distribution of the values in the range. For example, if you know they are uniformly distributed, or you know that they are all even, or they have some property, and profiting from this property, the attack can be made more efficient. I put here one example, and instead of dividing the interval in two, you can divide it into any number of pieces, and check in which piece the key is, and this can be used since our split detection algorithm not only tells you that the key is on the left or on the right, but also how many keys are in this interval between A and B. Maybe there are more keys, and we could generalize the algorithm to work with more keys and to attack them all in a same run of the algorithm. Finally, let me continue with this. Can this attack be extrapolated to other database management systems? Well, theoretically it can. Our attack is only dependent on the indexing structure and split detection, and since most of the commercial database management system use B trees or B plus trees, then in principle the attack could be made to work with these other database management systems. However, there's a lot of parameters that need to be taken care of, such as the optimizations that I mentioned, such as caching, journaling, and a lot of other parameters and inner workings of databases, which aren't explained in the B-trees papers of the 70s, nor in the present papers, and all this internal stuff needs to be analyzed very accurately for the attack to work with this. Finally, what can we do to stop this attack or to detect this attack? Can a run of this attack be detected during the attack execution or by reading the logs, making some forensic analysis? Well, a first countermeasure could be don't index data. Then every query will take the same amount of time, and this is very inefficient, and it's unlikely to be implemented, but in some cases it will help to prevent the attack. There's more realistic solutions or countermeasures which might work, and that's, for example, transaction throttling. Say, if in a given implementation a user isn't supposed to add more than 10 inserts or 15 inserts, then this can be blocked, say, from an IDS or from the web application that is hosting from the web application that connects to the database, but in different ways one can stop certain insertion behaviors. Also, applying some cryptographic blinding techniques or extrapolating the blinding techniques from the cryptography, one could encode somehow the values that are stored in the database, and in this way the values of the search keys cannot be guessed or are muddled up and are more difficult to guess. However, of course, this will imply a penalty in efficiency and might not be wanted. Also, introduce random delays so that two inserts that produce one insert that produces a node split and another one that doesn't cannot be identified. And this has also been done in cryptography, and it worked in realistic applications. And I think that's it. So thank you very much. And if you have any questions, I'll be happy to answer them.
Could you give one or more examples of like a real life situation where you would have rolled what kind of data in the table that you want to get, and then also the situation if you could really insert those keys individually?
Sure. Well, we executed the attack against search keys with different types of values. For example, 64-bit numbers and alphanumeric strings 32 values, was that? 32 character strings, and the attack worked with both. Actually, if the size of the values held in these columns is bigger, then splits are easier to detect. And about realistic applications, well, in principle, any web application that has a database in the back end and where a user is able to make inserts, for example, to provide your credit card number, could be used for this attack. However, we did not execute the attack experimentally against a web application, but always against a database as users. So even in a database where, for example, to speak of another situation where the attack could be implemented, if one user is allowed to make inserts, let's say in a commercial application that stores economical transactions where each time a seller makes a transaction, he can add the registers of his selling in the database, and he is not allowed to extract data from other operations, then he could execute this attack and make a lot of insertions and steal the data in the database. So, yes.
Because, for instance, let's say I could create users with a password in the database, right? And say that the password is then the index field. So I could start choosing passwords, and then in this way find a certain password in the database, right?
Yes, correct.
But then I still have the problem that I don't know what it's attached to, right, in the database.
You mean you don't know what's the user?
Yeah, I don't find the user with it, right? So I just find a password that fits this database.
Yes, of course.
I just try to replicate
Yeah.
a very cool attack.
Well, yes, you can do the same with the user, or also maybe you can more easily build a dictionary of users than a dictionary of passwords. So maybe the passwords are securely chosen, but of course the usernames are not securely chosen because they aren't supposed to. And once you guess a few passwords, you try them with a dictionary of usernames and.
And that's what you said, that you may be able to extend it to multiple values in the database.
Yes, of course.
Try and make a list of users in the database, and try and make a list of passwords, and then try
Yeah.
a combination.
Okay, thank you. Any other questions?
It seems like your attack is almost solely dependent on time of execution, and you stated clearly one of your assumptions was nobody else is on the database. My personal experience is that any kind of database that's going to contain enough information to be a worthwhile target, be that information health information or financial or just plain personal identifiable information, it's going to have many more than just one user at a time. So I would like to know more about your attempts to improve this in a